Our planet is in a constant state of flux. Forests shrink, cities expand, coastlines shift. And for a long time, trying to get a handle on all that change, across the entire globe, felt almost impossible. Well, not anymore. Today, we're talking about the incredible technology that's letting us read the Earth from space using artificial intelligence.
I mean, seriously, think about that question. How do you give a planet a health check? It's a massive undertaking. And to even get started, you need to be able to classify what you're seeing from orbit. That means getting clear on two really key ideas that sound similar but are actually very different.
So first up, we have land cover. It's exactly what it sounds like. The actual physical stuff on the surface of the Earth. Is it a forest, like you see here? Is it water, sand, ice, concrete? It's simply what the ground is covered with. That's part one. And here's part two, land use. This is all about the why. It's about human purpose. So the land cover here might be grass, but its use is for farming, right? For grazing animals. So if land cover is the what, land use is the how and why. And telling them apart is absolutely essential. Okay, so why does this all matter so much? Why are we so obsessed with mapping this stuff? Because when you track both land use and land cover, or LULC as scientists call it, you're basically creating a report card for the entire planet. And that report card is critical for figuring out what comes next.
And the applications here are huge. This isn't just an academic exercise. We're talking about managing emergency response after a fire or a flood. It's about planning cities that can grow sustainably. It's how we track climate change, protect endangered species, and manage precious resources like fresh water. This data is the bedrock for pretty much every major environmental decision we have to make.
So, what's driving all this change? Well, it turns out it's a two-layer problem. You've got what they call proximate drivers. That's the direct stuff, like building a new suburb or clearing a forest. But behind those are the underlying drivers, the bigger forces like economic policies, population growth, and new technologies. It's this whole complex web of cause and effect that's constantly redrawing the map of our world. So we know why it's so important to track all this. But how in the world is it actually done with this new technology? Let's zoom in on a really cool case study that pulls back the curtain on how we can teach a machine to see and map our planet. All right, so here was the mission. A team of researchers set out to create a ridiculously accurate map of the Jammu district in India. Now, this place is super diverse. You've got everything from rich farmland to dense forests and rugged mountains. It's the perfect test case. Can AI actually figure all that out from a satellite picture?
The process itself sounds pretty simple when you break it down. First, you grab the satellite imagery. Step 2, you have to train your AI. Using this amazing tool called Google Earth Engine, the researchers basically showed the AI a bunch of examples, saying, see this? This is a forest. And this is a river. This is a city. Then, you let the AI loose on the whole dataset to classify everything. And finally, the most important step, you check its homework to see how accurate it was. Now, this is where it gets really interesting. They didn't just use one AI. They set up what was basically an AI bake-off. They tested 4 different models, but let's focus on 2 of the main contenders. You've got Random Forest, which is a really powerful and complex model, and then you have CART, which is a much simpler classic algorithm. The question is, which one is better at reading the Earth?
And wow, the results speak for themselves. Just look at this. The map on the left was made by the Random Forest AI. See how clean and defined those different areas are? Now look at the one on the right from the CART model. It's messy. It's got this salt and pepper effect from all the misclassified pixels. You can literally see the difference in quality. But just how much better did the winner do?
Get ready for this. The Random Forest model achieved an overall accuracy of 99.36%. Just let that sink in for a second. That is an almost perfect score. It means the AI could look at a point on the map and correctly identify what was on the ground almost every single time. That kind of precision is a total game changer.
So here's the final scoreboard from the AI bake-off. You can see Random Forest is the clear winner, way out in front with that 99.36% accuracy. It also got the best Kappa score, which is just another way of saying the map it produced is incredibly reliable. The other AIs did okay, but none came close. The big takeaway here is that we now have a proven, best-in-class method for doing this work.
And that brings us to the most exciting part. Because what works for one district in India, well, what does that mean for the entire planet? This is where a small-scale study becomes a truly global story.
See, this wasn't just a one-off experiment. It's a blueprint for the future. You take free satellite data, combine it with powerful cloud computing like Google Earth Engine, and unleash a sophisticated AI like Random Forest. That recipe is repeatable, it's scalable, and it gives us a way to map change anywhere on Earth quickly and cheaply.
And it's incredible how quickly we got here. The first Earth-observing satellite, Landsat, went up in 1972. For decades, using that data was slow and expensive. But then, in 2008, everything changed. The US government made the entire Landsat archive totally free for everyone. That single decision unleashed a tidal wave of innovation that led us right here, to this moment of AI-powered real-time monitoring.
And this isn't some far-off future idea. It is happening right now at a massive scale. What you're looking at here is a land cover map of the entire United States, built using these exact kinds of methods. We've gone from mapping a single district to mapping a whole continent. We are creating the most detailed portraits of our planet that have ever existed.
So what does this all add up to? Essentially, we're building a dashboard for planetary health. Led by groups like NASA and the European Space Agency, we're fusing together data from dozens of satellites to get a complete picture. It's putting near real-time information into the hands of scientists and decision-makers so we can all become better managers of this planet we share.
So we've reached this amazing point in history. For the very first time, we can watch our world transform with the precision that was pure science fiction just a generation ago. We can see it all. We have this incredible new knowledge. So the final question, the one that really matters, is what are we going to do with it?